Hello, my name is Phil. I've studied chemistry for over 50 years, and I've taught college chemistry for over 40 years. Many years ago, I became interested in and then concerned about global warming and climate change. I studied these topics to better understand what is happening to our world. I felt I could save you some of the time to do the same if you have the curiosity and are willing to put in some effort of your own. I'm going to go straight through this video, but I don't recommend you do the same. I think it may work out better for you to watch this video in segments, and I have suggested 3 groupings up here that you might want to use if you choose this approach. Whatever approach you decide on, I do believe it is worth the effort to understand the greatest challenge the human race has ever faced. So we're going to tell a little story about global warming, fossil fuels, and us. If we understand how global warming works, we can better understand why we need to do something about it. And that is the challenge of this video. Global warming is increasing the Earth's temperature as a result of burning too much fossil fuels and extensive deforestation, which is adding too much carbon dioxide to the atmosphere. Other important greenhouse gases include water, methane, nitrous oxide, and a few others in low concentrations, but we're going to mainly focus on carbon dioxide, a little bit of water, a little bit of methane. There are many alarming consequences of excess carbon dioxide and other greenhouse gases in our world. Those tend to be grouped separately under a category of climate change, and there's really not enough time to talk about all those details in this presentation. We have 3 temperature scales in our world. In the 19th century, this was one that they invented. This came from, they had well-defined measuring points. They called the freezing point of water 0 degrees, and then 100 degrees was the boiling point of water. So they had 100 divisions between those, and those were the degrees Celsius. At the time, they didn't know about this temperature scale that would come about, called Kelvin scale. What the science found was that if they lowered the temperature down, 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 until they got to a point, there was no kinetic motion of the molecules in the atoms. And so they called this absolute zero. We cannot go below that temperature. It turned out that that was 273 degrees below the defined 0 point for the Celsius scale. So these are same size degrees in these 2 scales, but just a shift of 273 degrees difference. Excuse me. There's another temperature scale which really shouldn't be around anymore, but since the United States still uses this temperature scale, we have to include it. This one has the freezing point of water at 32 degrees Fahrenheit and the boiling point of water at 212 degrees Fahrenheit. That has 180 degrees between these two, and so 180 degrees Fahrenheit is going to be like 100 degrees Kelvin, which is 100 degrees Celsius. You'll notice, too, they don't put a little degree sign by the K for Kelvin. Now, it turns out that for the last 7, 8, 9, 10,000 years, Earth's temperature has been fairly constant, little fluctuation, but it's been around 288 degrees Kelvin. Okay, that would put it up here someplace. That turns out to be about 15 degrees Celsius, which is a pretty comfortable temperature, which turns out to be 59 degrees Fahrenheit, which is the same pretty comfortable temperature. So if you're familiar with those, you would recognize that. We're going to be talking about energy in this world, and excess energy is our problem. So we want a definition of energy and ways to measure it. Now, the common units of energy are joules, the scientific units, and then older units of calories, which we're not going to use, except just a brief mention of food calories. So our reference amount, as defined long ago, was 1 gram of water, which is the same as 1 cubic centimeter of water, which is the same as 1 milliliter of water, and it's all about the size of a sugar cube. Now, if this starts at some temperature, and we increase the temperature 1 degree Celsius, or 1 degree Kelvin, or 1.8 degrees Fahrenheit, originally that was defined as 1 calorie. Later, when they developed scientific units, like kilograms and meters and seconds, they redefined this as 4.2 joules. So the joule is the little tiny amount of energy. Since it's pretty small, sometimes they lump them together in groups of 1,000, which is called kilo. So if they had 1,000 little joules, they would call that a kilojoule. And that's how much energy it takes to make this temperature go up 1 degree Celsius. Now, we also have this idea of food calorie in our world, so we still use the name calorie, but it's not really a little calorie, it's a kilocalorie, it's 1,000 of those. And so that would be the same as 4.2 kilojoules, and that would be the same as 4,200 little joules. So we want to remember this. 1 food calorie is equal to 4,200 little joules. Now, all of these details up here are lumped together in one expression. That's called the specific heat of the water. It takes 4.2 joules to heat up 1 degree Celsius for 1 gram of material. So we'll do a little problem here just to see how it works out. We're going to look at an 8-ounce cup of water. We're going to heat it up to boiling from room temperature for tea or coffee or cocoa, something like that. Right away we run into a problem because our expression down here, specific heat, is in grams. So we need to convert our 8 ounces into grams. Turns out there's 28.3 grams, so we multiply that out. And instead of 8 ounces, we're going to have 226 grams. We're going to start at 25 degrees, which we call room temperature. We're going to take it up to boiling, which we call 100 degrees. And so there's a temperature difference of 75 degrees. Every one of these grams has to be heated up all of these degrees. And so we put that all into an expression here, and we can take our mass and cancel out with the 1 gram here, and the temperature and cancel out with the 1 degree Celsius here. And we come up with an expression that looks like this. And that's 71,000 little joules. Since we can group them together in the units of 1,000, we can also call that 71 kilojoules. Let's take a look at how fast energy transfers from one place to another place. We call that a rate, and that's something per time, in this case energy per time. Our little unit of energy is joules, and our time is going to be seconds. So this has a special name called a watt. So when you see watt, what you really want to be thinking is joules per second. How fast is the energy transferring? And watts show up in all kinds of places. So let's take this old guy here, and let's see if we can figure out how many watts this guy is putting out. We'll assume that this person is burning 2,050 calories a day. Well, first off, this is a food calorie. So that's like a kilocalorie. So we're going to have to use our little expression that we had on the previous page of 1 food calorie is 4,200 little joules. Okay, that will cancel out the calories. And then, because of our expression up here in seconds, we have to take days and make it into seconds. So we have 1 day for 24 hours, 1 hour for 3,600 seconds. And you can see that when we divide out these big numbers right here, it comes out 100 joules per second, which is the same as 100 watts. That's kind of interesting because you've probably seen light bulbs with 100 watt ratings on them too. Let's take a look at how we compare energy absorbed or given off by different objects. What we're going to do is we're going to standardize the area that we compare them so that everything that we look at is using the same amount of area. This could be energy in or this could be energy out, either way. And what we're going to use is 1 square meter. So we could call that as 1 square meter or 1 meter squared. And then we're going to be talking about the energy in terms of watts. Remember, watt is a joule per second. So joule per second per square meter. We're going to be looking at the sun and the earth as black bodies. So a black body emits energy based on its temperature. In this case, the sun and the earth. By definition, a black body is completely opaque and in thermal equilibrium with its surroundings. So it's going to have some temperature that's in equilibrium with the surroundings about it. A black body emits a spectrum of electromagnetic radiation, so that's a lot of big words, but basically it's a form of light. We're used to saying light is something visible that we can see, but the electromagnetic spectrum goes far beyond that. Okay, and that's going to depend on its temperature. So down here I have a black body. Here's its temperature, its black body temperature, and that's going to determine how much watts per square meter are coming out. All right, that's what we're going to look at. Now, we have a little formula that turns out to be really helpful to us called the Stefan Moltzmann Law, and it gives answers in watts per square meter, or it uses this value right here. It's a pretty simple equation. It just has energy is equal to some constant times another variable. So we only have 2 things we don't know here. We don't know the energy, we don't know the temperature. The constant, it's a funny looking number because it's got that exponent, depending how good you are at math. But it's just a number, it doesn't change. Very tiny number, and it has units to make everything cancel out so that the energy comes out as watt per square meter. You'll notice the temperature is raised to the 4th power. So it's temperature times temperature times temperature times temperature. That could be a pretty big number if you multiply those all together. So this is one way we could use the equation to figure out the energy, if we know the temperature. But we could turn it around. If we know the temperature, then we can rearrange the equation so that we have the energy divided by the constant, and we're going to take the fourth root of that. Don't worry if you don't know the math. You'll never have to do the math. Anything here, I'll just put the numbers out for you. Just want to show you that we can go back and forth between these two. So the important takeaway is, if we know the black body temperature in Kelvin, we can calculate the total energy in watts per square meter, or watts per meter squared. Okay, if we know the total energy, we can calculate the temperature. We can go back and forth. So let's take a look at the sun, and we're going to use the Stefan Moltzmann Law. The black body temperature of the sun is 5,800 degrees Kelvin. Whew, that's pretty hot. The actual core of the sun is about 16 million degrees Kelvin. We have a lot of nuclear reactions going here where we're fusing together 4 hydrogen nuclei to make 1 helium nucleus. And then that's generating all this energy with this enormous temperature. And it takes about 100,000 years for that energy to work its way out to the surface. And by the time it gets to the surface, it's 5,800 degrees Kelvin. It turns out that the radiation coming off of that is in the visible region. The main peak radiation is in the visible. And we can see this, of course. We know that because when we look at the sun, we can see the sun shining at us. So if I put that into the Stefan Moltzmann Law, I could figure out the energy. All right, so there's the constant. That never changes. Whew, this is a big number, 5,800 raised to the 4th power. So you know that's a huge number, but it's multiplied by a little number. But even so, it comes out a lot of energy, 64 million watts per square meter. That's what's coming off the sun. Right? Now, a square meter is just a tiny, tiny little part of the sun. Okay, the sun actually has a lot of square meters. If we figure that out, if we take the radius, we put it into this equation here, 4 pi r squared, we get that the sun has 6 times 10 to the 18th square meters. Every one of those square meters is putting out 64 million watts. So we multiply these two guys together, and that gives us the total energy coming from the surface of the sun. 4 times 10 to the 26th watts. Remember, that's joules per second. Every second, that much energy is leaving the surface of the sun. If you're interested in these funny names, that happens to be 400 septillion joules per second. We can do the same thing for the Earth. Of course, we know the Earth isn't that hot. If we look at the black body temperature of the Earth, it's about 288 degrees Kelvin, which I mentioned before. We can give that in Celsius and Fahrenheit. And it's been that way for several thousand years, 7,000 or 8,000 years, maybe as far back as 10,000 years. Now, we don't see this. This energy we feel as heat. It's in the IR region, infrared. So we feel this as heat. We could go through and calculate the total energy at all the wavelengths using the Stefan Moltzmann Law. But this time we put in 288 degrees Kelvin to the 4th power. So it comes out 392 watts per square meter at the surface of the Earth. Quite a bit less than the sun. Remember, that was 64 million. Now, we also have to multiply by the square meters on Earth, so we need the radius, and then the equation 4 pi r squared for the surface area. This time we get 5.2 times 10 to the 14th square meters. Every one of those square meters is putting out 392 watts per square meter. So we multiply those guys out, and we get 2 times 10 to the 17th watts, which is the same as 2 times 10 to the 17th joules per second. And if you're interested in those funny units, that's 200 quadrillion joules per second. Quite a bit less than the sun. Remember, the sun was 10 to the 26th, so we're quite a bit less. But still pretty substantial if you compare it to what we put out. We were only putting out about 100 joules per second. 100 watts. Now, how does the sun transfer its energy to the Earth, and how much energy gets transferred? Well, the sun, remember, is putting out an enormous amount of energy per square meter, 64 million watts per square meter. It's going out in all directions. We said that was about 10 to the 26 joules. But it's got to make a long journey to get to the Earth. It's got to go about 93 million miles. This changes a little bit, plus or minus. By the time it gets to the surface of the Earth, it's been diluted by all the square meters in this enormous sphere, and it's down to about 1,370 watts per square meter coming in at the surface of the Earth. Now, if the Earth was a flat disk, we'd say that the area was pi r squared, just the area of a circle. But in fact, the Earth is a sphere that's spinning around, and so when this energy comes in, it's hitting this spinning sphere when the area of that is 4 pi r squared. So we're going to take this area, this energy coming in, and we're going to divide it by 4. So per square meter, we're getting about 342 watts per square meter coming into the Earth. Now there's another little problem here, and that is the Earth has a lot of white surface. The North Pole, the South Pole, the tops of the clouds. And when the light comes in, it can be reflected away, and it turns out that about 30% of the light is actually reflected back out. It doesn't get absorbed by the Earth. This is called the albedo. Right? Now this can change. Say the North Pole ice melts and goes away. We're not going to reflect as much ice away. And so that'll mean the Earth absorbs more heat, and that'll mean the Earth gets warmer. So this is a little problem that we're going to have to confront in the future. All right, so we have now our 342. We're going to multiply that by 0.7 because that's the amount that actually makes it into the Earth and gets absorbed. That's 240 watts per square meter. Now this should get your head scratching. You should start saying, that doesn't make sense. You just told us that coming off the surface of the Earth, we have 392 watts per square meter. Okay, so that's part of the problem here. This is part of global warming that we have to figure out and understand. We're actually getting more energy coming off the surface of the Earth than the sun is providing into the surface. Now, the energy needs of all the humans, I'm just giving this to you as a fact, it's around 20 times 10 to the 12th watts. Some people say it's 10, 15, 20, someplace in that region. We'll just say it's around 20 times 10 to the 12 watts. This could be referred to as 20 terawatts, using tera for the 10 to the 12th that we see there. Now that's the total energy entering the atmosphere from the sun per second. Now what do people actually, this is what people actually need. What is the sun actually putting in? It's putting in 240 watts per square meter times the number of square meters. So the sun is giving us 130,000 terawatts, and our needs are 20 terawatts. So the sun's being very generous here. If we divide 20 by the 130,000, we only need 0.015% of the sun's energy to run all of our energy needs in the entire world. So there's plenty of energy from the sun, but the problem is it's just too dilute. It's spread all over the surface of the Earth. And the things that we do require a high density energy, like driving a car, flying a plane, driving a truck, cooking a meal on a stove or something. These are high energy, and we're not getting that from the sun. Now, what regions of the electromagnetic spectrum are emitted from the sun and the Earth? What do they look like? Well, this is going to depend on the temperature of the black body. So we said the sun is 5,800 degrees Kelvin, and the Earth 288 degrees Kelvin. The electromagnetic spectrum is right here. We have radio waves, microwaves, IR, infrared, visible, ultraviolet, X-rays, and we could go beyond gamma rays and stuff. So we're not going to really be interested in anything except these middle guys right here. Now for the sun, it's putting out energy at 5,800, and it turns out that that is mostly visible. Okay, this is the energy distribution coming off of the sun. And yellow is kind of like the peak energy right in here. There is a little bit of energy beyond the visible, beyond the violet of the visible. We call that ultraviolet. There's a little energy below the red. We call that infrared, and even down to the microwaves. All right. So this is what the sun's giving us as a black body. And remember, we said that was 64 million watts per square meter. Now, to try and write the IR energy here on this scale, this is just too small. So I just put a little line here to symbolize that. Let's take a look at what the Earth's doing. Oh yeah, so we're not going to use these energies, these parts of the electromagnetic spectrum in our talk. So I just want to focus on these. What regions of the electromagnetic spectrum are emitted by the Earth? So the Earth has a black body temperature of 288, and it's emitting its energy in the IR region as IR light, infrared. Right? And so this scale right here is much, much smaller than the scale in the previous slide. These are in hundreds, and the previous slide was tens of millions. And if we went down to the bottom end of the energy here, we would find the microwaves even much lower than the infrared. Okay, that'll be important later in our talk. So what we see with this particular temperature, using the Stefan Moltzmann Law, is that we're getting 392 watts per square meter. Remember, that's more than the 240 watts per square meter coming from the sun. Okay, and that's going to be a result of the greenhouse effect. Now, if this was supplying all of our energy, if we had no atmosphere and this determined what our temperature was, we could come down here and put it, actually we could come up here and put it in the Stefan Moltzmann Law and solve for the temperature. The temperature would be 255 degrees Kelvin. That would be minus 18 degrees Celsius or 0 degrees Fahrenheit. And you can see that's going to be pretty doggone cold for our world. Right? So this is not our world. Our world is really at 288, which is a much more warmer, much more comfortable world, at least in the recent 7 to 10,000 years. So let's take a look at these 4 regions of the electromagnetic spectrum. The ultraviolet is the highest energy part. If you'll notice over here, I have the energy scale. So here's the kilojoules. Remember, these are thousands of joules. And we go up and we get up to about, in this range here, 600 plus or minus some kilojoules. And this is a very large amount of energy. In fact, strong bonds inside of us can be broken if you put in more than 400 kilojoules. This is well above 400 kilojoules. And so ultraviolet light is actually dangerous to living organisms because it can damage the bonds in their structure. And so we have to be very careful with ultraviolet light. It can be damaging to life on Earth. We're fortunate in that nature helps protect us a little bit, but we have to be careful too. If we come down a little bit in energy, okay, visible, we're at 200 kilojoules plus or minus a little bit. And there are some weak bonds that can break with this amount of energy. But also this does some other things that don't actually break the bonds. But in any case, this is a lot less energy than what we see up here with the ultraviolet. Okay, this happens to be where our eyes work. Our eyes can see this energy coming into them. Breaks a pretty weak little bond in our cell membranes and causes a nerve impulse to our brain. So this is a very valuable energy to us, but it's not real damaging to most of the bonds in our body. If we go down even lower, we get to infrared. Notice the red here is the low energy end. You might remember from high school or elementary school, red, orange, yellow, green, blue, indigo, violet. Sometimes they say Roy G. Biv. These are the colors of the rainbow that we typically talk about. Anyway, if I go below the red, our eyes fail. Our eyes can't see below the red, but they also can't see above the violet. So these energies are there, but we don't detect them with our eyes. But if we go down below, this is called infrared, and you can say it's pretty low energy. We're not going to break any bonds that are 400 kilojoules strong with 10 kilojoules down here. But what this energy right here can do is it can make the bonds stretch and contract more. They vibrate faster and faster. Or they can take bonds and they can bend relative to each other. So this has caused the molecules to have their bonds vibrate and bend. They absorb that energy, and that energy gives them that ability. If we went down even lower, we would come to something they call the microwaves. And now it's not even a full kilojoule. It's just like a tenth of a kilojoule or so. And what this energy can do is it can take a water molecule and make it tumble around, spin and rotate and turn and twist around and around. And that turns out to be pretty important. And you probably already know that because you probably have a microwave that you've used to cook food with. Now, you'll notice I put per mole on all these guys. And a mole, since the molecules and atoms are so small, we can't really see them. If we group them all together in a very, very big number, we can see them and work with them and study them. And so what we do is we take this number right here, 6 times 10 to the 23rd, and we call that a mole. So when I come over here and I say a mole, I'm saying 6 times 10 to the 23rd. Now, you've already done something like this, because a lot of times you probably go down and say, I'm going to get a dozen eggs. You're not saying 12, but you know that that means 12. Right? And don't forget that kilo means 1,000. So let's take a look at visible light first. We'll just take a little feature of each of these, because these are important. We want to understand them a little bit. This is life's most important electromagnetic radiation. It causes photosynthesis to occur. It causes us to be able to see, vision. So I just have photosynthesis here as an example. Now, we get our energy from the sun. Comes at us. It's giving us ultraviolet, visible, IR, microwaves. It's giving us all these energies. But this part that comes in here is visible, right? Now, the visible light can come over here, and it can use the energy of light can be used by the enzymes in the cells to combine carbon dioxide and water, pretty complicated series of reactions, and then it can crank out carbohydrates and oxygen. So carbohydrates give us food, and oxygen allows us to breathe and combust that food. So then what we do, and other animals and plants even, is they take those carbohydrates, mix them with the oxygen, and then they burn them to give carbon dioxide and water. And you'll see that's exactly what we started with here. So this truly is the circle of life. Okay, these go round and around. And so that sunlight is giving us the essential things that we need to live on Earth: food and oxygen. When the electrons come in, they cause this complicated molecule with some other things associated with it to excite an electron, and then those electrons move around and in the end make these things right here. Now, the chlorophyll that we see right here absorbs on the ends of the visible. So it absorbs in sort of the violet region and absorbs in sort of the red region, but not in the middle. So if you look at the spectrum right here, this part is being absorbed, this part is being absorbed, this part is coming through. And if you look at that, that looks pretty much like green. That's what we see as the leaves. Right? Now, remember, we're exciting something. The energy is actually exciting an electron to move around, and then that's coming over here, it's being transferred to something else and causing a chemical reaction. So the energy can be released either by causing a chemical reaction or be released as heat. We'll see it done both ways. Now, ultraviolet is very important to us, even though you might not know exactly why, but you've probably heard that ultraviolet at the surface of the Earth is dangerous, and that's because we said it has so much energy that's in the troposphere. However, ozone, ultraviolet is helping us in the stratosphere, protects us, but ozone down in the troposphere is bad for us. So with photosynthesis, we make oxygen. Oxygen can diffuse across the barrier. We break up the atmosphere above us into layers. The closest layer is the troposphere, 7 miles. If we go beyond that, then they call that the stratosphere, and there's other layers above that we're not going to worry about. Okay, so the oxygen that's made at the surface of the Earth with photosynthesis diffuses into the atmosphere. It's pretty much everywhere, but it can cross this little barrier that we have, and when it gets into the stratosphere, it's getting up to where these ultraviolet photons are coming in. So if these ultraviolet photons were to reach the surface of the Earth, we probably wouldn't be here. It would be too dangerous. But instead, what happens is some of the ultraviolet photons hit the oxygen, split it apart into oxygen atoms. They combined with oxygen molecule and put 3 of them into a single molecule called ozone. Now, the ozone, turns out, can absorb a different photon, and then it just relaxes, so it generates heat. So it gets excited, relaxes, gets excited, relaxes, gets excited, relaxes. This can do it over and over. And so that's going to protect us. These ultraviolet photons are not reaching the surface of the Earth because they are absorbed up here to cause a chemical reaction or to cause excitation and then heat. Right? Now, down at the surface of the Earth, we do have ozone, and that is not a good thing because the ozone molecule is a very reactive molecule and can attack biological molecules. So this comes from nitrogen oxides and volatile organic compounds and things like that. That's not the purpose of our talk. But we do have ozone at the surface, which is dangerous. The next energy we're going to look at is the infrared, or what we call IR. Now, just because we can't see it doesn't mean it's not important. The IR energy is very important, central to our talk today. It's especially good for bending and stretching bonds of water, carbon dioxide, and methane. You'll notice these all have 3 or more atoms. That's very helpful for absorbing the IR. There's other molecules in the atmosphere, nitrogen and oxygen and argon, and these don't absorb IR, so they're IR inactive. So we're really interested in the carbon dioxide in the water. Carbon dioxide bonds can bend back and forth, and the way they do that, they get that extra energy, is from the IR, the infrared. The bonds can also stretch, contract, so they can stretch symmetrically or asymmetrically. All this takes energy. And so the IR adds in the energy, molecule gets in an excited state, and then it gives that energy away by bouncing into some other neighbor molecule and transferring it, and then it's back at the ground state, and it can do it again, and then it's back Do it again and again and again. This can go on many, many times. The molecular collisions we see in the atmosphere are going on at about 10 billion times per second. So this kind of transfer of energy around and around and around is super, super fast. Okay, so the water molecule gets excited, bumps into the nitrogen molecule, gives the nitrogen molecule the energy, gets relaxed, and it does it again. All right? Now, it turns out that light coming through the atmosphere is transparent. So the light just passes right through, just like glass. We know that glass doesn't absorb because you can look right through glass and see everything outside perfectly. So the light passes through, the visible light. But once it gets inside, say, something like this is a greenhouse, it hits the surface that we have down here, the green, the brown, the color of all these different things, absorbs some of that visible light. And then once that happens, these objects down here irradiate that energy as IR, as infrared. So once it gets in here, it's infrared, and then that infrared can make all these things happen with water and carbon dioxide and all that stuff. But it cannot get through the glass. So the infrared gets trapped inside here. Okay, so it just keeps circulating, circulating, circulating. There'll be a low diffusion of heat out, but it takes a while for it to work its way through the glass. This could also happen in, say, a truck or a car that you left out in the parking lot. Probably you've done this a few times yourself. You have all the windows rolled up. It's a hot day, so let's say it's 85 outside. But inside the car, the truck, it's super hot. Sometimes it's so hot you got to open the door and wait. The steering wheel's too hot to touch. So this could be quite hot, 140 degrees. If there was a little animal in there, that animal probably would not survive. So we have to be real careful about that. They call this visible light coming in shortwave because it has shorter waves. And then once it gets trapped inside here, it goes through the window, hits the surface of the seat or the upholstery or the carpet or whatever, and then it gets reabsorbed, re-emitted as a longer wave, the IR light. And so we could see something like this. Now, these two situations are not really the situation of the Earth, because this is all sealed off. This is a closed system. If the windows are up, this is a closed system. But what if we rolled the windows down a little bit? If we rolled the windows down a little bit, then you can get heat, some of the heat leaking out the way it does at the edge of the Earth. Since the edge of the Earth just goes out to outer space. And so the temperature might be a little bit cooler. It'll still be hot. Okay, it's not 85 degrees like it is outside. So we're looking at 118 degrees Fahrenheit. But it's not 140 either. So it's something in between. This is more like what the Earth is. And then the last example here is the microwaves. So you might say microwaves there. That's the slow energy. We said that was 1/10 of a kilojoule. But what these are really good at is they're really good at making the water molecules flip and spin and twist and turn over and over. So they excite up tiny, tiny little bit of energy. But then that energy can be transferred to things around it. So what is around the water molecule inside a microwave oven? It's the food that you have in there. So the food's going to have carbohydrates and proteins and fats. And so you're exciting this water molecule, and then it bangs into these other molecules, these biological molecules. Well, it gets relaxed. But the carbohydrates, proteins, fats, they get excited. And then you do it again to the water, it bangs in again. Keeps pounding over and over and over. Gets hotter and hotter. Now, in a microwave, you usually have an idea about how much heat you want to put in. So you put in a time. As long as that microwave's going, that microwave oven is working, it's putting in microwaves. But then when you stop, it stops. So we're adding in energy, transferring. Adding in energy, transferring. Adding in energy, transferring. And then we finally say, hey, the food came out just the way we wanted. Okay, our popcorn is just right. So we stop. Now, if you're going through this talk, this is a good place to stop if you want to take a break. Or you can keep going. We're going to keep going. We're going to take a look at the composition of the atmosphere in parts per million. So we're going to say the air has a million parts. That's 100%. Now, most of that is nitrogen gas, about 78%. And a pretty large chunk is oxygen. We'll say it's about 21%. You can see just a little bit short. And then about 1% is argon. Okay? And that's all we're ever going to say about argon. It's an inert gas. But none of these guys absorb IR energy. None of them absorb IR light. So those guys are over here. Now we also have a lot of other things in the air. The main ones we're going to look at are water, carbon dioxide, and methane. Now water fluctuates because 70% of the Earth's surface is the oceans. And so water could be pretty high. It could be maybe 10,000 parts per million. Or you might be over a very dry desert where it's hardly anything at all. And so we're just going to call it sort of an average of 2,000 parts per million. So it sounds like a lot, but remember, we got a million parts, so this is really kind of tiny. Carbon dioxide until recently, till the last couple hundred years, has been around 280 parts per million for most of Homo sapiens development. Right? This is a very comfortable amount of carbon dioxide for our world. It gave us that comfortable temperature. But notice what's happened in recent times. We're currently running about 420 parts per million. So we don't know for sure is this significant or not. We're going to find out. We've gone up quite a bit, almost 50% increase. And we're going up every year about 2 to 3 parts per million. It's getting more and more, so probably we're approaching more towards 3 parts per million now. So this is going to get bigger and bigger and bigger as the years go by, unless we do something. And then we have methane down here. Right now it's just under 2 parts per million, about 1.8 something parts per million. But it was about 0.7. So we have also increased the amount of methane in our world, about 2.5 times from what it used to be. Now the problem with this is methane is 80 times stronger greenhouse gas than carbon dioxide. Now sometimes you see people say, oh, that's only at the start. Over 100 years it disappears and it's not that much. But you know what? We just have sort of a background amount of methane that's about 2 parts per million. Okay, it may be disappearing, but we're adding it in. So it's 80 times stronger IR absorber than carbon dioxide. So even though we only have a little bit, say I multiply 2 times 80, that's 160. We're talking here, 280 going to 420. So we're talking 160 versus 420. Now there's other things out there. Ozone, that absorbs IR. We're going to ignore it. Nitrous oxide, that also absorbs IR. In fact, it's I think 300 times stronger at absorbing IR, but it's a very tiny amount. And these other ones right here, that we're going to just ignore them. So if we come down and look at what is the amount of carbon dioxide for all the other gas molecules, carbon dioxide is only 1 out of 2,400 molecules in the atmosphere. That's 0.042%. Sounds like nothing. Okay, 0.042%, I don't know. Look at water. Well, water, we had 2,000. That's still pretty tiny. It's 1 out of 500. That's about 0.2%. But water fluctuates. It could be a little higher. It could be a little lower. And there's nothing we can do about this anyway, because we have 70% of the Earth is the ocean water. And then we have methane. Used to only be about 0.7, but now it's about 2. That really looks small. 0.002%. Okay. So this looks like almost insignificant. But remember, we multiply this one times 80 to get its IR absorbing power. Now, what is the main greenhouse gas? But as I said, nothing we can do about that. Carbon dioxide, we have control over that. We're cranking it out like crazy by burning all the fossil fuels. And then we have the other greenhouse gases. And we're just going to assume not a big deal right now. But the methane could become a big deal. We have to think about that for the future. Now, the amount of water in the atmosphere depends on the temperature. Okay, well, if the temperature is going up, then the vapor pressure of the water is going up, and it's going to get more water in the atmosphere. That's going to absorb more heat, so that's a little bit of a problem. We call that a feedback mechanism. Anyway, there's nothing we can do about the water. It equilibrates with the oceans in a few days. Now, the problem of carbon dioxide is it stays in the atmosphere for a long time, hundreds to thousands of years. All right? And so anything we do now, it's like it's going to be there for a while. So we have to think into the future for this problem right here. Otherwise, we're going to put so much carbon dioxide in there, and then we're going to be stuck. Now, when carbon dioxide warms the atmosphere, it's going to retain heat. And then when we retain more heat, that makes the vapor pressure of the water go up, and we put more water in the atmosphere. And so then that further increases the temperature, and then this is called a feedback mechanism. It gets hotter and hotter. So carbon dioxide is kind of a trigger. It can start things happening. Now, in moderation, carbon dioxide is great. Okay, we just came out of an ice age, about 20,000 years ago. And if it wasn't for some of that carbon dioxide, along with some orbital effects, we would be in an ice age. Okay, but we're not. We're in a very comfortable temperature right now. But if we put in too much carbon dioxide, then that's bad, because it overheats the world. We need just the right amount, just the amount we've had for about 10,000 years. So we don't want to go up, we don't want to go down. Carbon dioxide, it's only 0.04%. Is that even possible to have some profound effect on the climate of the Earth? Well, let's take a couple other good examples. Say in 49 states, if your alcohol is 0.08%, they're going to throw you in jail. If you're out driving a car, that's a DUI. If you live in Utah, it's only 0.05%. So a tiny little amount can be pretty significant. What if you were breathing air that had only 0.02% of hydrogen cyanide? Well, you'd be dead in 10 minutes. So a tiny little amount doesn't mean it's not important. And if you consider the carbon dioxide itself, 0.04%, what does that do? That feeds all the plants and the plankton on Earth. And what do those guys feed? They feed all the animals on Earth. So this tiny little amount, not even all of that, it's just part of that, feeds everything on Earth. And what could be more profound than that? So just because it's a tiny amount doesn't mean it's not important. And this is just, again, to show you that carbon dioxide isn't all by itself. There's methane out there. And if we look at the warming effect of these, it would be 72% carbon dioxide and 28% methane. But we're ignoring the water. So this is kind of like a picture of our atmosphere. Really complicated, So many molecules up there. This is just a little symbolic representation. So all these molecules are moving in all directions, up and down, front and back, left and right, really fast. And they're colliding with other molecules 10 billion times per second. This is like a foaming, fermenting stew of molecules banging into each other. Visible light comes in. The atmosphere is transparent, comes to it with no problem, but it hits the surface of the Earth, or it hits the water. It gets absorbed. And then that energy that it had is re-irradiated as IR, which we call heat. So that's coming off here. Now, a little water molecule coming down and hitting the surface gets excited. Okay? And then when that molecule gets excited, it hits another molecule, transfers the energy, but then it's back to being just a water molecule, which could get the surface again. Carbon dioxide could hit the surface, get excited, hit another molecule, transfer its energy, relax back down, and then do it again. A methane molecule could hit the surface by the IR heat coming off, get excited, hit another molecule, transfer the energy, and relax back down and do it again. Molecules that are excited up in the atmosphere can hit other molecules, and they just bounce the energy around here and here and here, all over the place, okay, spreading that energy around. And that's going to happen really fast, and the sun is shining on all the surface of the Earth every single day, someplace. Now, the water molecules that get excited are in equilibrium with the liquid water in the Earth, the oceans, the lakes, the rivers, and streams, and so forth. So that happens really fast, just in a matter of days. But the carbon dioxide lasts a long time. Methane only lasts about 10 to 20 years, and then it gets converted into carbon dioxide. But during those 10 years, it's 80 times stronger as an IR absorber. So it's doing some damage down here. So remember what's happening. We're absorbing an IR photon and getting into an excited state. We transfer that kinetic energy that it has to other molecules and gets relaxed. And so now the energy is out there dissipating into, say, the oxygen, okay, or the nitrogen. And then it does it all over again. And these things are banging into each other 10 billion times a second. Okay, this is all going on real fast. So even though the carbon dioxide is only a tiny little bit, remember it feeds everything on Earth. It feeds the plants and the animals. Let's take a little analogy here. I like to play pool, and maybe you do too. But we'll use a little pool analogy to show how a single little factor can drastically change the energy of a larger, more complex collection of items. So let's look at the pool balls. They're sitting on the pool table. There's one cue ball sitting by itself down at one end, down here. Then all the other balls are at the other end, all racked up, sitting right there. Okay. Then you are the sun's energy. You pick up the cue stick. The cue stick is the photon. You pull it back and slam it into the cue ball. The cue ball is the IR, the carbon dioxide, the water, the methane. You're going to transfer the energy to whatever the cue ball is. The cue ball transfers its energy to all these other balls, these other 15 balls. It slams in there, and they go all over the place. It's just a mess. Some of them, if you're lucky, maybe goes into the pocket. Okay. Now you keep playing the game, but when you play the game, you only strike one ball. Okay, you keep picking up the cue stick and slamming it into the cue ball. Okay, you never once hit any of the number balls. You just keep hitting the cue ball over and over and over. But as the game progresses, the balls are going into the holes, the balls are getting moved all over the table until the game's over. And then what do you do when the game's over? You take all the balls out, you rack them up, and you start another game. It's like the sun comes around the next day to shine on the earth. It's just like a brand new day. And so that's what's happening with the earth. When the sun shines down, sends the visible light in, it generates IR energy at the surface of the earth, which cause the water, the carbon dioxide, and the methane molecules to transfer their kinetic energy into the atmosphere again and again. So this is a little bit complicated slide here, but I just wanted to look at sort of the distribution of this energy around the world. So we already mentioned this again, but here's the sun sending out, we're going to say 342 watts coming in, but 30% is bounced out. So that's bounced out by the atmosphere, say the clouds, or the surface of the earth where it's white, the North Pole, the South Pole. Okay, so that's not going to warm up our earth. So what's actually coming in is about 240 watts per square meter. Okay, part absorbed by the atmosphere. There's ozone molecules up there, other things that can absorb the light. And then part by the surface of the earth. But you'll notice the surface of the earth is not getting all of the energy. Okay? It's sort of spread between the atmosphere and the surface of the earth, although it's getting the bulk of the energy here. Now, when it gets absorbed, then it's re-irradiated as IR heat. So it goes up and it hits these other molecules and causes them to get excited, and they transfer their energy into the atmosphere. This cycles around and around and around. But you'll notice some of the energy is coming back down. When a molecule gets excited, it doesn't just go up, 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 and it's out. Okay, that would be if there was no atmosphere. But if there's an atmosphere, it goes up and down. Some of it comes back down, or left and right, or front and back, sort of stays in this layer right here. Okay, so some of that heat comes down and gets reflected back in. So we're adding to this over here. And so what actually is coming off is what we calculated from the temperature of the Earth, which we said was 288 degrees. So we're getting off about 392 watts. Now, part of this energy is going in to make things happen on Earth. So we have like ocean currents, we have jet streams, we have hurricanes, tornadoes, clouds, latent heat. This is the heat evaporation of water. Okay, these are all coming from this little excess energy right here. It's sort of retained in the Earth. But by the time we get up to the surface of the interface of the atmosphere with space, we're just leaking out the same amount of energy that was coming in. So we're getting in about 240. We really can only leak out about 240. If we got in more energy here, then we would have more energy inside here, and then we would generate a higher temperature before we leaked it out. And if we got in less energy, the energy would be less leaking out, and we would have a colder world. So the world can change its temperature, hotter and colder, depending on how much it's actually absorbing here compared to what's leaking out on the edge there. So just remember, if our temperature was only based on 240 watts per square meter, we're way too cold. We're just a big giant ice cube. But because of this effect of absorbing and redistributing the energy to all the other molecules in the atmosphere, we have a warming effect, and so our world is really like 288 degrees Kelvin, based on the 392 watts per square meter at the surface. So I call this one a blanket analogy, all right? Let's say you were laying in a bed, you just laid down with your body without being covered, and you might say, it's a little bit chilly, so what do? You go over and you grab a blanket or a sheet and you put it over the top of you. Okay, so when you don't have that sheet on, you're just leaking the energy out from your body. There's nothing to put it back towards your surface of your body. But if you put a sheet over the top, yeah, you're still leaking out some energy here, but some of it, before it leaks out, is coming back and sort of adding to the energy of your body and making you warmer. If it still felt a little cold, you could go over and grab another blanket, put that over the top, and retain a little bit more energy, so you feel warm, even though it's even colder. You're trapping more of the energy. And that's sort of like what's happening on Earth. So the Earth has these layers of atmosphere, which we could call blankets. And if there's more of them, we retain more of the energy. And if we have more carbon dioxide and water and methane, they hold in that energy. They're like the blankets, the layers that we need to keep ourselves warm. But if you put on too many blankets, you get too hot, and then you have to take off a blanket because you're kind of cooking. So how fast is the temperature and the carbon dioxide changing now, where we are, compared to recent geological changes? So we have down here a little plot. Okay, so we're going to have temperature is going to be blue, atmospheric carbon dioxide is going to be red. That's, if we look down here at the scale, you can see, ooh, this is a lot of years. Sounds like a lot to us, but this is nothing compared to the history of the Earth. The Earth's 4.5 billion years old. We're only going out about 400,000 years. But if you look at it, I have it grouped in like groups of 100,000 years, because it looks like we're going down in temperature, down in carbon dioxide, and then we're going up, and then we're going down, and then we're going up, and down, and up, and down, and up. Okay? And notice how they follow each other so closely. When the carbon dioxide gets low, like here it's down to about 180 parts per million, started at 280, then the temperature gets real low. So over here we're talking about maybe between 0 and -8 or so. Okay, so the temperature goes down when the carbon dioxide goes down, and the temperature goes up. And this happens on about a 100,000 year schedule, something we're going to look at in just a minute called the Milankovitch Cycles. So that's a main driver of changing the temperature. Now when the temperature's down here, this is Celsius we're talking about, this is pretty doggone cold. Okay, in fact, the world is covered in a lot of ice when something like this happens. They call this an ice age. The ice goes all the way down to say, the top of America or into Europe. It's just a lot of ice. But then when it warms, okay, we go up to what they call an interglacial period. We're in between the glacial ice ages that we're talking about. All right? Now, the last one, this is 0. This is where we are right here, 0 years. We came zooming out of this maybe about 20,000 years ago. And then we hit this spot, and you'll notice, wow, it's pretty flat. Temperature just looks like it stayed right here. Kind of different than these other ones. This is something kind of special. Well, people were around. Homo sapiens, they say, might have been back as far as 200, some people even say 300,000 years ago. So if that was the case, that means we actually lived through an ice age or two, and somehow we survived, but we didn't really have the ability to develop civilization. We were surviving. We weren't growing crops. How can you grow crops when the temperature is like freezing cold? We were maybe catching animals to eat. Anyway, once we got up here to this flat part, things kind of changed. We had this very comfortable time, and people started being real creative. They developed agriculture and animal domestication, and villages and cities and language and writing and religion. This is where our human civilization developed, at this sweet spot right here. Now, that was all working fine up here. This is the time interval right here. But you notice this little dot. That little dot indicates the Industrial Revolution. About 250, 270 years ago, we figured out a steam engine, and that we could burn fossil fuels, say coal, then oil, and then gas. We could burn that and make really dense, concentrated energy that allowed us to do stuff. And look at what happened. Carbon dioxide had been high of 280, low of 180. Okay, that went on. You could go back millions of years, and it never went over really 300 parts per million. And all that time, 2-3 million years. And then humans come along, we start burning fossil fuels. And watch the carbon dioxide go up, 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 up. Okay, can't even put it on this chart. We're at 420 right now. So it's off this slide right here. And we're not stopping. It's still going up and doesn't look like it's slowing down any. So you can see how carbon dioxide and water follow each other. And so what people are saying is the world's getting warm. All the little ice cubes, the North Pole, South Pole, Greenland ice, with time will melt. Right? Now those are pretty big ice cubes, so it takes a long time for those guys to melt. But they're going to melt if we keep doing what we're doing. But it'll take a long time. Now if we look at the change in temperature here with time, just from nature's own effect, looks like nature warmed up about 8 degrees over 20,000 years. So that's not very fast, 0.0004 degrees Celsius per year. If we were living back here, we wouldn't even notice. But nature doesn't care, because nature just goes on for billions of years. So we got up warmer even at that slow rate. Now, those 100,000-year cycles are referred to a lot of times as being due to the Milankovitch cycles. And so there's 3 little variations of this. One is the orbit of the Earth. It's circular, and then it goes to elliptical on a cycle of about 100,000 years. Now this ellipse is really exaggerated. It's just a little bit off on the ellipse from the circular. But what it does is it makes the Earth a little bit closer at one time and a little bit farther away at another time. So if the Earth's a little bit closer and the North Pole's pointing towards the sun, it can be a little bit warmer in the summer, and that'll keep away the Ice Age. And just the opposite, if it's going to be an actual Ice Age. Then it gets a little colder in the summer and we start to build up ice. Another thing that can happen with the Earth is the tilt. It's not spinning perfectly a straight line. It goes back and forth, tilting a little towards the sun, a little away from the sun, back and forth, back and forth. So again, if it tilts towards the sun, it could be a little bit warmer. The crucial time is the summer time, the ice in the summer. And then it can actually wobble like a top. So all these 3 things together, this is about a 100,000-year cycle, this is a 40,000-year cycle, this is a 20,000-year cycle. These all cause the Earth to get warmer or colder and cause the ice ages that we were just looking at. But notice that the carbon dioxide is reinforcing that. Now, how fast does the temperature change? Well, we just said that it was 0.0004 degrees per year. Let's take a look at what happens in recent times. So this little graph goes back to 1880, not too long ago, about 140 years ago. And so the temperature, notice it's just bouncing around a little bit. It's always below this kind of a 0 point line that we've defined here. So it's not real warm, but it gets up there to 0. Every once in a while, it went up a little above here. That's kind of an anomaly, but if you look when it happened, it's like in the 1940s. We were having a World War then, World War II. So it might be that we were generating a little bit extra energy at the surface of the Earth because of the war. But that's just speculation. Now we could go back about another 10,000 years, and we were in this climate sweet spot where we developed agriculture and all the other stuff. So it hardly fluctuated, just a little bit above, a little bit below throughout this whole time. And then all of a sudden, we come to 1970. All right. So if you come up here and look at the data, these are by decades, 80s, 90s, 1900, 10, 20, 30, 40. And then when we get up to 1970, we never hit another negative number. Look at all these negative numbers here. But 1970, we get a little bit above 0, and then we start going up. We're always above 0. This is every single year now, 91, 92, 93. Above 0 all the way, and it keeps getting bigger. Okay, down here it's like 0.3, and here's about 0.5, and here's about 0.6. Okay, and then look at what happens in the most recent years now. In 2014, 0.7, 0.9, 1.0. Okay, we're definitely going up, up, up in temperature. It takes a while for the temperature to change, and the temperature is still going up. All right. So if we start right here, let's say 1970. Let's say we go all the way up to right here, 2020. That's about 50 years. All right. So what I did here was I said 50 years, it went up 1 degree. That's about 0.02 degrees per year. We're going to compare that with the 20,000 years that we went up to 8 degrees. And it comes out we're heating up the world 50 times faster than we did coming out of that last ice age. That's a big deal, big difference. And notice that temperature's never coming down. It's going up and up and up and up and up. We're sitting right here, and this is what we're looking at in front of us, going all the way up there. Now, there was a little decrease right here because they had a volcano erupt. The second biggest eruption in the 20th century was Mount Pinatubo in the Philippines. And when the volcano erupts, it spits out a lot of sulfur dioxide. And sulfur dioxide actually blocks the visible light, scatters it. And so the temperature doesn't go up as much. It has a cooling effect. But it washes out with water real quick. So after a couple years, it's all washed into the ocean as sulfuric acid. And then once it's gone, carbon dioxide just starts heating up again. It's always there heating. So that's where we're sitting right now. Now, if we kept going out to this point right here, you'll notice this is 1.5 degrees above our 0 point. This was the target goal for the 2015 Paris Accords, where they said we can't go above 1.5 degrees. We have to protect the Earth from warming up too much. So it looked like that was our goal, but if you follow the line, since we haven't done anything, in fact this year we're increasing more than we did last year, then it looks like we're just going to hit that line. And if we come down, might hit it around 2040 or so. If we didn't stop, we just kept going, we come up here, and everybody always talks about 2100. Even though things are going to happen after 2100, they talk about it. 2100, they wanted to be below 1.5. But instead, we would be probably around 3 degrees up from this point. This is a tremendous amount of energy. This excess energy that we're looking at, we would be doing that 3 times over. 1, 2, 3. And you can just see around the world today the extreme types of things that are happening. The storms, the fires, the hurricanes, and things like that. So this is something we don't want to do. Now the carbon dioxide is changing fast, just like the temperature is changing fast. Temperature lags a little bit because it takes a while for it to heat up. So what are the recent carbon dioxide changes in the last 40 years? So again, we're going to kind of do the same thing. I have here 1770 because we could just keep going and going and going for 3 million years. We'd never be over 300 parts per million. But around, 1770, we started burning fossil fuels, coal, and very, very slowly we started coming up. Also, we were cutting down trees, we were burning up forests. All that stuff was affecting it in a slow way, not like the rate that we're doing it today. So if we go back, say 190 years, we went up about 40 parts per million. That's just 1 part per million in 5 years. That's a pretty slow rate. If that's all we did, we probably wouldn't be worried about it right now. But it's not. So if you look at what the divisions are here, these are 5-year intervals. So 1960 to 65, excuse me, 65 to 70, and all the way down 5-year intervals. And you can see it's going up. Instead of being about 280 before the Industrial Revolution, now it's 320, and then up here it's 350, and then it's 385, and now we're up at 420. And you can see each 5-year interval is getting bigger. Here's about 3, here's about 5, here's about 7, here's about 9, here's about 10, here's 11, here's 13. We're not going in the right direction. Okay, we're adding more and more. And so currently, if we follow just in this last part right here, and this part's really known accurately, because back in 1958 they set up a little station on the top of Mauna Loa volcano in Hawaii to measure the carbon dioxide in the atmosphere. And so it was at this point right here, and then it's going up and up and up. Okay, every single day we measure this carbon dioxide. So if we just kept going, here's 2020, if we just kept going, we'd be going up like this. Well, people got concerned, and so they had that 2015 Paris Accord. And they said, please, please don't go over, some amount of temperature increase, 1.5. And so what they hoped was we'd quit burning fossil fuels, the carbon dioxide would slow down. By 2030, we'd only want to be doing this about half as much as we were. And then by 2050, we want to totally stop it, shut down all carbon dioxide generation. So we hit this flat spot. We still have some problems with this, but at least the problems would be more controllable. Now, if we don't do anything, we're going up about 3 parts per million per year. So if we take a 10-year interval, that's 30 parts per million for every 10 years. 20, 30, 40, 50, 60. If we get out to that 2100 magic dividing line, we would be at 660 parts per million, assuming we just keep it at 3 and don't go up to 4. Right? There's going to be more people on the Earth. They want to have a higher standard of living. So that requires dense energy. And if we start using all that energy, we'll get even higher than this. So this could be higher. 660 could be 700. Now that would predict a tremendous increase in temperature. 3, 4 maybe. The disaster totally would be 5 degrees. Anyway, that's what we're hoping doesn't happen. So our goal is to cut all the fossil fuel use by 2050, cut it down to about half by 2030. So these are kind of the same plots. The only one I wanted to add in different right here is sea level. So here's the carbon dioxide. Remember, it's going down, it's up, it's down, it's up. 280, 180, 280, 180. And here's the temperature. So the temperature is up a little bit higher, say 2 degrees or something, down -8. Temperature is following it along just like that. But what happens when all of the ice melts? Well, that water has to go someplace. So then if you come down here and look at sea level, that means sea level is going to be pretty high. So they're calling sea level, say, an interglacial period, the water level at an interglacial period. And you can see all the way across, that's what we're going to reference to for 0. Now, if we go into an ice age, the water in the ocean starts to freeze out and becomes gigantic glaciers that cover all the northern hemisphere, and so the sea level falls. And look how far it falls. We're talking 300, 400 feet. All right, this is an enormous amount. Could you imagine sea level dropped 400 feet? Of course, we'd be in an ice age, so it'd be pretty uncomfortable. But then it melts, and so all of a sudden it comes back. Sea level rises 400 feet, then it drops, and then it rises, and then it drops, and it rises. So right now, we're at this stage right here. So this is just a normal cycle right here, but we're pumping in carbon dioxide like crazy. So when we got down here, we didn't start to fall back down. Instead, humans started generating incredible amounts of carbon dioxide, and we're shooting up. Okay, and it's possible we could hit 700 parts per million by 2100. Right? That's going to make the temperature shoot up. It's lagging a little bit. It's already gone 1, but we probably built in 2 for sure, possibly 3 if we're not careful. So that's going to go up. That's going to melt the ice even more. So we have ice in Greenland. 15% of the ice on Earth is in Greenland. 85% of the ice on Earth is in the Antarctic. Now the Antarctic's pretty protected. It's going to be hard to change the temperature, but things are happening down there. But Greenland is more dynamic. The Greenland ice is changing fast. And so it's possible that Greenland could melt. The whole thing wouldn't melt probably for 300 years, maybe longer, 400. But even if it melts a little bit, it can raise the sea level quite a bit. We don't have to raise it much to be a disaster. If all the ice in Greenland melted, the sea level would go up 22 feet. So that's a problem. All right, so the past millions of years, the Earth has cycled through these ice ages and interglacial periods, mainly because of the Milankovitch cycles, but also carbon dioxide is superimposed on top of that. Now, there was a period about 55 million years ago that's kind of like what we are today in terms of the amount of carbon dioxide that could be there and the temperature. This was called the Paleozine, Eocene thermal maximum, or PETM. Carbon dioxide at that time was 1,000 parts per million. Remember, we were talking possibly getting up to 700. And the temperature was 5 to 8 degrees Celsius warmer. So that means right here we'd be going up in temperature pretty warm. And so at that time, it melted all the ice on Earth. There was no polar ice. In fact, the poles were tropical. They had alligators and palm trees and stuff like that. And the sea level was 250 feet higher than today. Okay, that was the warmest period in the last 65 million years. And it's possible we could be doing something like that. Now, also, they feel that the oceans were very acidic back then, which was very damaging to life in the ocean. So that's another problem that could happen. Now, this is a real quick turnaround. Only 100,000 years this happened. But once you get that carbon dioxide in the atmosphere, nothing you can do. You can't stop it. Now, throughout Earth's history, we've had changes in carbon dioxide level. And a lot of times it's because of volcanoes blowing up. Say a volcano blows up. So there's stuff in the earth that's going to come out with all that lava that blows out. And that could be, say, fossil fuels, coal vein, or oil well, or something like that, oil pocket. And so that could blow out carbon dioxide and methane, and that would heat up the Earth. So sometimes that's actually been a very good thing, because the Earth has been pretty cold at certain times. They had a period, 600 million years ago or so, called it Snowball Earth, because the entire Earth was white. It was surrounded by glaciers and snow and stuff. And so it reflected all the light. It was trapped. So they figured that the way it got out, and this might be due to plate tectonics, is they had a really violent era of volcanoes blowing out carbon dioxide, methane, and that probably helped the Earth escape that Snowball Earth, which was good for us, because then life could march again forward. But anyway, how do humans compare with this volcanic activity that we're talking about? Because some people have said it's not really what we're doing, the volcanoes are doing it, okay, but that's not even close to being true. So Mount Pinatubo erupted in 1991, second biggest volcano in the 20th century. Now, with it came sulfur dioxide, and sulfur dioxide actually cools the atmosphere, but it only lasts for a few years, 2 years, 3 years, 4 years, and then it gets washed out by the rain back into the oceans. And then whatever the carbon dioxide and methane is, that starts to heat up again. Now, what humans have done is they've went around and they've searched for all these little pockets of fossil fuels, the coal, the oil, the natural gas, and wherever they find them, they stick a little straw down into the earth and suck it out. And so we have over 1 million of these types of situations where we're just sucking out the fossil fuels. Right? Now, those fossil fuels are basically prehistoric solar energy. These are like dead plants and plankton and little microorganisms that have been pushed down into the earth and heated under pressure and reformed as fossil fuels. So this is a tremendous amount of energy from the sun. It's like a bank account, and you went down and you just withdrew all your money at once and went on a spending splurge. Okay, that's what we're doing here. Those deposits were made over hundreds of millions of years. Okay, geologically stored solar energy. And it's just like we went over to the stove and we just turned the stove up full blast. Okay, whatever on top of that stove is going to get cooked. And that happens to be our Earth that we're talking about. Now, where's all this carbon in our world? So it's kind of like a distribution of carbon. Look at a carbon cycle. So first off, when we talk about carbon, we could talk about just the carbon part or the carbon dioxide. I'm going to talk about the carbon dioxide part. When we do, we talk about big amounts. Giga means a billion. That's 10 to the 9th. And then we're going to put a ton behind it. So we're not talking about gigamoles of carbon. We're talking about gigatons of whatever it is we're talking about. Now, in the atmosphere right now, we have about 3,200 gigatons of carbon dioxide. It's really hard to even think in numbers like this. Now, some of this was already here just from the natural balance of nature, but humans have come along and we've added maybe about 50% of what we had before. We've increased it by 50% of more gigatons from burning all the fossil fuels. All right. Now, this carbon dioxide gets spread around the world. So some of it's going to be in equilibrium with the oceans. So the carbon dioxide is going to be in equilibrium. We're going to add to that. That'll make the oceans more acidic, unfortunately. But there's already a lot of carbon dioxide that's going back and forth. We're just adding a little bit more. It's also involved with the plants, okay, because the plants use carbon dioxide as food. Remember, that's how we built up our carbohydrates and the oxygen. And then at nighttime, the plants actually use their food for themselves, but then during the day, animals can eat it. We eat the animals that eat the plants. And so it supports a whole life structure based on this. But we're adding a little bit more to that from the amount that we're generating. If we come over here, this is actually what we're doing. We're sending down our little straws into the earth, and we're sucking out the gas, the oil, the coal. And there's still a lot down there. If you look at all this, this is the reserves. All these gigatons are still there. Look at this is what we added, 1,100, and we're in trouble. We better be careful. We don't want to add 4,000 more. Okay, 2,000 more. We're done. We're toast. But right now, what we're doing every year, we're blasting out about 3,500 gigatons of carbon dioxide. from the oil, the coal, the natural gas. Now, there's this other factor here that we're adding in. This comes from the fact that we're chopping down trees. We're burning up the Amazon rainforest. We're chopping down the trees so that we can grow soybeans to feed cows so that we can eat steaks. Right? But if we add that in, that means altogether we're taking out about 40 gigatons, and about half of that's going to stay in the atmosphere. Okay, about a fourth of that will go to the oceans, and about a fourth of that will go to vegetation. We'll grow a few more plants. Plants are really helping us out here, but not enough. Okay, the oceans look like they're helping us out, but there's this downside. It's when carbon dioxide dissolves in the water, it makes carbonic acid. So it's making the oceans more acidic, about 30% more acidic because of that. Now there's carbon dioxide all over the place in the earth. I mean, not carbon sources that can turn into carbon dioxide. The most dangerous one that we're concerned about is the permafrost. Because the permafrost is basically frozen old plant material. And if that starts to warm up, then microorganisms can start to chew it up. And they can put out carbon dioxide, and they can put out methane. And so if this gets out of control, look at their 6,000 gigatons. Even if we added a little bit, we're already concerned about 1,100. If we added 100 out of this, or 200, or 500, that's going to magnify this tremendously. So we're really, really concerned about this. This is what we call a tipping point. All right, so as humans, we've distorted the balance in nature. Okay? And we're deforesting everything. We're cutting down and burning down trees. Currently, we're adding 40 billion, but it's going up. It's getting higher every year. Carbon dioxide spreads all throughout the atmosphere, but it also goes to the oceans and the plants. Okay, so this is where we gotta be careful. This is a distribution of the carbon in our world. Again, this is a good place to take a break if you are going to go through the whole thing. So we'll start up. We'll keep going. What I'm going to look at now are the three types of fossil fuels that we talk about. The natural gas, which is mostly methane. We'll say it's methane. The oil, we're going to call all of the oil octane, just to make it easy to analyze things. And then the coal is super complicated. We're just going to call it all this strange molecule. We'll call this benzopyrene. So these are specific molecules that we can use to do calculations with. But really, these are complicated mixtures. Now, if we come down here and look at how they react, each of these guys reacts with oxygen. We do the same thing in our bodies with our carbohydrates and stuff. We combine the oxygen with the carbon and make carbon dioxide. We combine the oxygen with the hydrogen and make water. Now, if you look at methane, there's only one carbon. So, only one carbon dioxide. Octane has 8 carbons, 8 carbon dioxides. Benzopyrene has 20 carbons, 20 carbon dioxides. So just looking at that amount right there, you can see it looks like there's more carbon coming out because of the coal. Again, this is a balanced equation. We're looking at 1 mole of each of these guys. That's just a number, 6 times 10 to the 23rd. All right, think of a dozen, think of 12. And when we do that, we make a lot of energy. If we look at the energy from just this 1 carbon, it's almost 800 kilojoules from 1 carbon and the water. So methane has a lot of carbon, 75% in it, but not as much as octane, not as much as coal. Now if we look at octane, it generates a lot more energy, but then again, it has 8 more carbons. So it makes sense that it makes more energy, and it has more hydrogens. If we look at the benzopyrene for coal, we make even more energy, because it has 20 carbons, okay, but we're putting out 95% carbon here. That's not going to be as good. Now, the other downside of coal is it's really dirty. Okay, it has heavy metals like mercury. Mercury's spread all over the world because of so much coal that we burn. It also has sulfur, which can make sulfur dioxide, which causes acid rain, sulfuric acid. That generally rains out pretty quick. What about hydrogen? We didn't even talk about hydrogen. So hydrogen, this is kind of like our dream, our fantasy, that someday we could use hydrogen instead of all these guys up here. And people are working like crazy. You can see this car right here. It's running on hydrogen. There's countries doing this, Japan and Germany and even in California. So people are working on this, but right now it's not real practical. Hydrogen's a tiny little molecule. So you can see we're not getting a lot of energy out of one of those, but it is tiny. So let's take a look on the next slide. So what we're going to do to kind of even things out is we're going to pick the same amount, same mass of each of these materials. We're going to pick 1,000 grams, 1,000 little grams. That's about 35 ounces. That's about 2 pounds, 3 ounces, just for you Americans out there. Okay, so we're going to convert this to moles. How many of these little units, amounts, do we have? So 1,000 grams of methane, hey, we got a lot of moles because it's a small molecule, 62 moles. And the octane, 114, it's a little less. We only got 9 moles of the octane, but it is a bigger molecule. And the benzopyrene, we only got 4 moles of that because it's such a huge molecule. But look at the hydrogen. It's only 2 grams per mole. We got 1,000 grams. That's 500 moles of hydrogen. Whoa, that's a lot. So how much energy is released with each of those? Well, we used those energies on the previous slide. Every mole of the methane is going to give us almost 800 kilojoules of energy. So that's about 50,000 kilojoules. And if we have 9 moles of octane, 5,000 for each, 5,000 kilojoules for each mole, you get 45,000. So even though this is a bigger molecule, notice it's a little less energy for the same amount of mass. And if we look at the coal, way more energy per mole, but even less energy for the 1,000 grams, the same mass. But now look at the hydrogen. It had the tiniest little amount of energy in combustion, but we had 500 moles, 120,000 kilojoules released with the same amount of mass in each case. So hydrogen looks fantastic, although it has these problems that we haven't figured out yet. These are the energy densities per gram. You can see hydrogen looks the best, and then methane. So how much carbon dioxide is released? This is, we want to stop this carbon dioxide. Okay, that's warming up our world. Well, remember, methane was 75% carbon, and octane was 84% carbon, and benzopyrene was 95% carbon. So if we combine those, if we take the carbon amount and multiply it times the amount of carbon dioxide per gram of carbon, okay, we get about 6 pounds of carbon dioxide made. So that's a lot of pounds of carbon dioxide. Remember, each 1,000 grams was about 2 pounds, 3 ounces. And now we're cranking out 6 pounds of carbon dioxide. But in the case of octane, we're cranking out about 7 pounds of carbon dioxide. In the case of benzopyrene, we're cranking out about 8 pounds of carbon dioxide. So not only does it have a lot of dirty stuff, it also liberates way more carbon dioxide using coal. But now look at hydrogen. 0 carbon, 0 pounds of carbon dioxide. So if we could use hydrogen, it generates the most energy and no carbon dioxide whatsoever. And that's why people are working so hard on that one. Now what we're going to do is we're going to use octane as a stand-in for all of these fuels, just so we can do an energy calculation in a lot easier way. So it's not going to be exactly correct, but it'll be close. So how much fossil fuel does humanity burn in a year? How much energy does it make? Does it produce? Well, we're going to start with an assumption that last year we generated 40 gigatons of carbon dioxide. Giga is a billion, that's 10 to the 9th. It's released to the atmosphere, okay, dispersed in vegetation, air, water, land. We're going to assume all the fuel was octane, right? C8H18. Just like you see when you go to the gas station, you see there's an octane rating. So there's some octane in gasoline and other stuff. We're going to convert all that mass into carbon dioxide. And they're going to use that carbon dioxide, convert it to moles. And then we're going to use this balance equation right here. When we know the moles of carbon dioxide, we can figure out the moles of octane. Right? Now, when they say gigaton, okay, giga is a 10 to the 9th, but the ton they're talking about is a metric ton, so that's 2,200 pounds. So let's take a look. The mass of carbon dioxide would be 40 gigatons times the amount of pounds per ton times the amount of grams per pound. We have 4 times 10 to the 16 grams of carbon dioxide. Well, that's good, but we need moles up here. So we have to convert this to moles. Therefore, we use 1 mole per 44 grams. Okay, we divide 44 in there. We get about 9 times 10 to the 14th moles of carbon dioxide. It's about 910 trillion. Well, that's this right here, but what we really want is the amount of octane. So notice this is a 1 and this is an 8. So I have to take 1/8 of this, okay, 1 mole of octane per 8 moles of carbon dioxide. And so we get about 1 times 10 to the 14th moles of octane that we burned. Well, we know what energy is released when we burn octane. We said earlier that 5,000 kilojoules per mole, we have this many moles. So that means we generated 5.5 times 10 to the 17 kilojoules of energy from burning all those fossil fuels in a year. That's a pretty mind-boggling number in terms of energy. But what we want to do is we want to make it into joules. We're doing everything in joules in this talk. And so I have to multiply by another 1,000 little joules times a kilojoule divided by a kilojoule. We get 5.5 times 10 to the 20 little joules. So it's a number beyond our imagination. Now, is this what is warming our world? Well, we have to do a little bit more to figure that out, to test that idea. How much energy is added to the world every year from a 1 degree increase in temperature? Now, this almost sounds ridiculous. 1 degree increase, how could it compare to the energy we just calculated? But we're going to do it for 2 degrees and 3 degrees also, just to see. So now remember, just in your mind, watt is a joule per second. Now we had that Stefan Moltzmann Law that said we could figure out temperature if we knew energy, or we could figure out energy if we knew temperature. So in our case, we know the temperature. We're going to stick that in. We already did this problem. And that's how we got 392 watts per square meter based on this temperature. But if the world temperature goes up 1 degree, then we'd have to put a different temperature over here. And that would be 398 watts per square meter. Well, that's 6 watts different. That doesn't sound like very much. But remember, it's per square meter. And we're talking an entire year. Let's see how it turns out. So here is the area of the Earth, 5 times 10 to the 14th square meters. And here's the number of seconds. Okay, it's about 32 million seconds in a year. So we need to put these in there. Here is our 392 joules per second per square meter. Times square meters times seconds, we come up with, this is a big number, 6.52 times 10 to the 24 joules. And then we do the same thing at 289. It's also a very big number. All we did was make this 398 instead of 392. Now we've got 6.62 times 10 to the 24 joules. And when we first look at that, that looks pretty small. That's only 0.1 difference between these two. Now another thing is, we just know the temperature and the heat and the energy. We don't know why the temperature went up. And so that's places where we are falling a little bit short. So there's other things that we have to consider why a temperature would go up. But we're just attributing to, carbon dioxide, the methane, everything that's in there. So if we now compare these two energies that we figured out, the energy at 289 and the energy at 288, we get 0.1, but what we forgot is times 10 to the 24. So take one of those 10s and multiply there. We get 1 times 10 to the 23rd joules. If you were interested, that's 100 sextillion. So that is a lot of energy. So we're going to use this number to represent all of the energy inputs. The carbon dioxide, the greenhouse gases, anything else that's involved. So this would include other factors, Milankovitch Cycles, sunspots, volcanoes. But these guys aren't changing as fast as we are. All the stuff that's happening to us is in 50 years. The Milankovitch cycles are in tens of thousands of years. They've studied the sunspots over many, many cycles and found that they don't even affect anything. Volcanoes, we don't have any big volcanoes going on. It's pretty rare. So the only thing that correlates with this massive amount of energy is really the greenhouse gases over the last 100 years. Now, if we took that amount that we just figured out up here, so that's the 1 degree difference, all this extra energy from 1 degree, and then we went back to that number we thought was so big, burning all the fossil fuels in 1 year, how much energy did it liberate? 5 times 10 to the 20th. you can see that the amount of energy from 1 degree increase is about 180 times bigger than burning all the fossil fuels. And this is sitting in the atmosphere. This carbon dioxide is just sitting there day after day after day. Every day the sun comes up, it warms up. Year after year after year, the carbon dioxide lasts for hundreds to thousands of years. So we're going to add this in every single year for hundreds to thousands of years for that 1 degree increase that we increased up there. Well, what about 2 degrees and 3 degrees? So I just did the same calculation at 290, at 291, and you can see the watts per square meter keeps going up, right? And so if I calculate it out for all the square meters and all the seconds, these are the numbers we get. And so the difference in energy from our starting point, this one was pretty big, 1 times 10 to the 23rd, but if we put in an extra degree, it's about double of that. And if we put in another degree, it's about triple of that. Right? So the ratio to our year of combustion is 180 to 1, but then it's 350 to 1, then it's 530 to 1. You can see why we don't want 3 degrees increase, because that means year after year we're going to keep adding this amount of energy from the sun coming down and shining on all those carbon dioxides, exciting them, spreading their energy into the atmosphere. So you can see I put over here danger zone. Now what if this went on for 10 years? Say we're at 1 degree. We just added 180 times the energy of all the combustion from all the fossil fuels. If it went on for 10 years, we'd multiply 10 times that. That would be 1,800 times the energy over that 10-year period. What if it went for 100 years? That would be 18,000 times the energy from that 1 year of fossil fuel burning. And if it went on for 1,000 years, you might think that's not important, but we're thinking that there would be people 1,000 years from now. We're hoping that we don't destroy the world. That would be 180,000 times the energy over that period. So it's a tremendous amount of energy to keep adding in, and you can see it goes up. If we go to 2 degrees or 3 degrees, these numbers just get magnified, say 100 years, 35,000 times the energy, 53,000 times the energy. 4 degrees, 5 degrees, 6 degrees. 4 degrees is a temperature they are realistically talking about for the year 2100 if we don't change anything. So it would be even bigger than the biggest number that I have here. So we don't want to do this because there are things in the world that can get out of control. Thawing out the peat, the permafrost that we have in the world. Melting ice off of Greenland, melting the Arctic ice that's up there. Accelerating the ice melting in the Antarctic. These are things that can cause a lot of problems to people. So one last point. Deforestation, I haven't really talked about much about that, but that also adds carbon dioxide. When you chop down a tree, it starts dying and it converts to carbon dioxide and water as it decomposes. When you start a fire to burn up a patch of forest so that you can plant crops, that puts out carbon dioxide. All right. So this is a big problem. This adds a significant amount. Deforestation in Indonesia, the Amazon rainforest, the diversity there is incredible. We're just burning it up. We've had record fires in the western United States, Australia. Everybody probably remembers that a couple of years ago. Siberia never stops burning. It's burning year-round. The boreal forest of Canada and in Russia, Greece, Turkey, Portugal, Sweden, all these guys have had record fires. And they're all adding carbon dioxide to the atmosphere, just like cars and trucks and planes. Now, China and U.S. are number 1 and number 2 emitters, mostly because we're burning a lot of fossil fuels. But Indonesia, Brazil, they don't burn nearly as much fossil fuel, but they're destroying their forest. Okay, and so they're in the top 20. We got to attack this with all different approaches. Now, I thought up a little experiment. A lot of this stuff is so vague. It's like 100 years, I'm not going to even be here. So what does that actually mean? You can do a 5-minute experiment, and you can show yourself how climate change works. Get yourself 2 bags of popcorn. So what I did was I got my 2 bags, and then I put 1 bag in my normal way, which is I heat it up 1 minute and 40 seconds. This is the way the popcorn came out, and in fact I ate that whole bowl of popcorn. It looks good, tastes good, everything's good. Okay, what am I using to do that? I'm using microwaves. Whoa, microwaves? They're even tinier than infrared. Okay, people are saying infrared can't do all this. Well, look what microwaves did. Okay, and we all know this. We've all cooked with a microwave oven. So what's happening? Well, the molecules get excited. The water molecules, they bounce around, they spin, they twist, they turn, they bang into the food molecules, the fats, the carbohydrates, the protein. And they transfer their kinetic energy to them, and then they get relaxed. Well, you're just piling in the microwaves. Okay, you run it for a minute and 40 seconds. So you add more, it gets excited. It hits the molecules, relaxes. Again and again and again. These collisions occur, in billions, over billions of times per second. You're just pounding on those molecules and heating them up. And so we can cook food with microwaves, even though it's an incredibly low amount of energy. Well, let's do a little experiment now, and let's heat it up for 50 extra seconds. Okay, that's hardly anything, 50 seconds. Well, that's what I did. And when I did it, this is what came out. That's very different looking popcorn. Big chunk of charcoal right in the middle. And all I'm using is these tiny little microwaves. But I just kept pounding again and again and again. Okay, and then the carbs, the proteins, the fats, they started breaking down because the temperature was getting too hot. And so we destroyed the food there. So this is pretty much what we're doing to our world. Right? We have too much carbon dioxide, and what it's really good at is absorbing the infrared energy, which is 100 times bigger than the microwaves. And then, of course, we have the entire Earth. The atmosphere has tons of carbon dioxide, and we're doing it really slowly, but fast on geological time. Now, the popcorn is just a little tiny pack, and we can make all that happen in a minute and a half. Okay, the Earth is a lot bigger. We're using higher energy, IR, but it's taken a long time. Okay, we're doing it in tens to hundreds of years because of the amount of carbon dioxide we're adding. Geologically, this was usually over a period of thousands, tens of thousands of years. We've just accelerated the schedule. All right, so that was a little experiment that you can try out. Global warming is just the beginning. Okay, there's lots of stuff to know. I'm not going to go through all these. If you want to take a look, you can take a look. I just want to mention there's consequences of too much carbon dioxide in the atmosphere. And you can see some of those consequences here. I didn't write them all down. There's more than that. Climate change has tipping points. This is what we are afraid of right here. A tipping point is the threshold beyond which large change is initiated, and many times it's irreversible. We can't stop it. Feedback is where something has a self-reinforcing loop, comes back and it makes it change even more. And then if you change it more, it might go even faster. So you can accelerate the tipping points that we're looking up here. So these are melting all the Greenland ice, melting the Arctic ice, things like that. And there's more of these too. Now there's things we can try to do. Climate change mitigation means avoiding and reducing the emissions of these greenhouse gases going into the atmosphere. So we have to do things that help us stop what we're doing. Stop burning fossil fuels. Stop deforestation. Okay, so there's a whole list here. And again, this is only a partial list. And then there's adapting. Okay. Things are happening fast and bad, so we got to adapt and figure out how to reduce the negative impacts of those things. And take any advantages we can. Say there's new opportunities like solar energy, wind energy, things like that. Maybe there's other things that we can do that will change the way we live. And so there's a lot of possibilities here. All right. Now, this last one, climate engineering, they've had a lot of things suggested that are probably kind of scary. We probably wouldn't want to do it because it's a one-time experiment. We're experimenting on ourselves and we don't know what the outcome is. Now, the only thing that seems like it could make sense is sequestration of carbon dioxide. And they're trying to do this like crazy, but they're doing it on a very tiny scale, and it costs an incredible amount of money. So maybe something can happen if we keep working, but right now it's not working very well. Some oil companies have figured out how to pump carbon dioxide back into the ground, but what do? They use it to push out more oil. So if we figure out how to play with this card right here, maybe we can help ourselves. We have to take carbon dioxide out of the atmosphere to save ourselves. So, as I say here, there's difficult trade-offs. Okay, we want things, but we need things. So what are we going to do? We have to really satisfy our needs rather than our wants. The other thing is, we're going to have to work together. This is a worldwide problem. And then how are we going to pay for it? It's got to be the rich people that pay, because they're the ones with the money. The poor people are they're just getting hammered. So there needs to be a mechanism for worldwide collective action. So far that hasn't happened, but it's got to happen. We've got to get together to make this happen. So I just want to thank you for watching, and that's pretty much the end of the talk. Appreciate it. Bye-bye.